Well, good morning, everybody. As we discussed in the previous class, we'll continue for some more time with the introduction to digital communication systems, so that you understand what are the major issues in the design of a digital communication system and certain other issues. So, to start with, I'll again pick up a very simple block diagram, which you can see, wherein we have a transmitter unit and a receiver unit separated by a communication channel. Is that readable? Okay, fine. As an example only, we are considering as if a wireless communication channel, wherein I have indicated two antenna, but it need not be like that really. Most of the discussion that we will have should be general, so that you can apply the concepts in other communication systems as well. Now, our basic aim is to understand the various modules and subsystems in this whole system. Obviously, the system consists of the transmitter unit and the receiver unit, and also very importantly the channel in between. In fact, I try to bring in the notion of networks or systems, wherein a system may consist of several blocks or subsystems. So, if we are trying to understand the design and other features of a digital communication system, it is perhaps imperative that we have to understand how we should design the transmitter. We must understand how to design a very good quality receiver, and to do these two we must understand the features of the channel. Okay. This issue of channel and its contributions will come over and over again during our discussion. Okay. Now, to it is perhaps a common sense approach that we try to understand the starting point in our communication system, that means the transmitted unit. Okay. So, to build that, I am making use of the subsequent block diagram. Okay. And there you can find that I have drawn two blocks. Okay. It will continue further. The first block I am calling as a signal or message source. Okay. Signal in our context is known to be the electrical manifestation of a desired physical parameter. Okay. You should give me an example of a signal for our context. Any example of a signal as you understand in this context? Yes. Human speech after conversion into an electrical form, maybe at the output of a microphone. Okay. It may be available in the form of a current variation or a voltage variation, isn't it? That is the signal we are referring to really. We would also like to call it as message, implying that it has got something interesting in it which you would like to convey, transmit from the transmitter to the receiver really. Okay. So, the first block is a signal or message source whose output, if I now think of the electrical features of that really, whose output I can say is at least some kind of electrical signal. Is that okay? So, the output at point A is an electrical signal. Okay. Should we know any other feature of this signal or message? Should we study about, or should we be interested about any other feature of this electrical signal that we can expect at this point A? Bandwidth. Okay. Anything else? Yes. Power, bandwidth. Anything else? Louder please. DC level, then voltage or current. Yes. Statistical characteristics. I think that is the most important point. Yeah. See, in this course we are not going to discuss about the transducers, the principles of microphone, etc., etc. That is understood, I believe. Our starting point of interest will be that the signal that will be available is some kind of electrical signal, okay, definitely restricted to certain bandwidth. Okay. So, bandwidth is a parameter of interest. So, let me note that. How much is the bandwidth is a valid question in relation to the signal at point A. Okay. Then the statistical features of this signal. That means the signal is expected to be unknown. Okay. It is expected to have some kind of uncertainty, so much so that by observing a signal for quite some time, we may not be in a position to predict or guess what the signal is going to be for some more duration in future. That is a very obvious property of any signal really. Okay. So, I will write in short statistical features, whatever they are. One must try to understand before I can say that, well, I understand the signal, and this being the input commodity to our transmitter effectively, I must know the limitations and advantageous features. Incidentally, power is an issue, okay, when you actually design the system, but otherwise it is not so important for understanding the overall working philosophy of the system, isn't it? What is expected is that the transducer will be so chosen that the signal will be within a good operating range of the transducer, and the signal will be of good quality, so that processing it further should not be a problem using the devices that you choose. You may choose a transistor BJT based circuitry subsequently, or FET based circuitry, or any other electronic circuitry. The point is that the signal should be so nice that further processing is not going to be problem. Okay. But otherwise power etc. is not much of an issue. Okay. Usually the power, if you try to compute the power of signal at this point, is not very high, it is a low power signal, and that is what is sufficient. That is what helps in designing the subsequent circuitry. You can design low power circuitry subsequently. Okay. And power becomes an issue whenever we have to transmit the signal from one place to a distant place really. Okay. We will see that later on. So, the signal is some electrical quantity with some amount of uncertainty or randomness, so that we are interested primarily in its statistical features. Okay. We should also know about the bandwidth or the frequency range over which the signal is available. Fine. What can I say that it is an analog signal or a digital signal? There was a question at, some time back really. There is no restriction at the point at this moment really. The signal may be analog, the signal may be digital. Okay. So, I am now encouraged to draw the next block, which is, I am calling it as a block or subsystems which will do the job of sampling, quantization and associated coding if the signal is analog in nature. Does it make sense? Sampling is known to you. So, if the input signal is analog, things should be sampled, okay, and after sampling we would like to represent it using some binary or MRE or non-binary sequence. So, it needs some kind of quantization, fine, and after quantization we get a level which is somewhat different from the sampled value because of quantization up to finite levels, and then for more convenient representation we would like to bring in a binary or non-binary sequence, and that is the coding part which I am indicating here. Okay. So, if the input signal is analog in nature, then the usual operations that may be carried out in the second block, I am noting them as sampling, quantization and associated coding for better representation. Okay. And if the input signal is digital, that also should be acceptable to a digital communication system, and then it is obvious that we need not go for this kind of analog to digital pre-processing operation of sampling or quantization. Yes.
Any parity has to be added.
Well, we are open. We will add that whenever we understand the need for adding that parity. Okay. Yes, parity and many other things. Whenever we find that yes, that may be necessary, we will do that. At the moment, in this block, it is not necessary. It is not necessary. What we are doing primarily is we are conditioning the input analog signal. We have got an analog waveform which is varying randomly. So, we are trying to represent it in a more convenient fashion, so that we can get a digital signal. We have already discussed what a digital signal is, a discrete amplitude signal, okay, and many a times a discrete amplitude, discrete time signal. Okay.
Which is already coded, or do we need to code even if it's a digital signal?
coding is has a broad sense in the context of digital communication. See, I have mentioned about some coding, but I am saying that this coding is only in relation to a better representation of the samples, quantized samples. Okay, we will also use the term coding in some other different context. Okay, when we go further beyond the second block, is that okay? The job of this module, as I am trying to put it, is to do some kind of pre-processing on the analog or the digital signal that has been available at its input, so that things are better understood, so that we can go for more interesting and more involved signal processing, and ultimately can make the signal ready back for transmission at the output end of the transmitter. Okay, fine. So, this one can also label as a pre-processing unit, pre-processing unit. Okay. For an analog single channel input, the usual operations are sampling, quantization and coding. This coding now is a part of analog to digital conversion only. Okay. If there are multiple inputs at this block, that may be the case. Okay. Multiple users, they want to transmit through the same transmitter. In that case, there will be separate or well designed arrangement for sampling each of the signal, quantizing each of the signal and then putting them together. Okay. If the signal is available in a digital form, then we do not have to go for further sampling or quantization. Okay. If it is available in the binary form, which is the commonest form of signal, digital signal, okay, in that case what we may need is some kind of formatting here and there. In that case, the signal will be available in some high low format, okay, which I can interpret as some logic levels, fine. And if there are multiple users, we may have to accept sequences, binary sequences from each of them, do some amount of processing. We will have to maybe put some marker so that I can identify which bit is from which source and things like that, so that we can put them in order. Okay. And then this operation I am broadly calling as formatting, okay, for digital signals. So, depending on the type of the signal, analog or digital, this kind of pre-processing should be done. Otherwise, there is a chance that subsequently things may get mixed. Okay. So, we are keeping individual features of the signals, and then if it is an analog signal, we are converting into a convenient digital format. Okay. Any question at this point? Fine. Let us go ahead. Now, this output of this pre-processing block, can you just tell me, can you just give me some features of this output at this point B? Is it still an analog signal? No. Okay. So, this is a digital signal invariably, okay, irrespective of whether the input was analog or digital. So, I can say the signal here is digital, digital electrical signal. Okay. Any other property would you like to say, talk about? For example, we talked about the bandwidth of the basic signal at point A. Can we find some relationship of the bandwidth of the signal at point B? Should there be some relationship? Yes. Okay. That depends on the sampling rate, the rate at which I am finding getting the samples really. Okay. So, yes, one can talk about the bandwidth of the signal at this point. Okay. And the bandwidth should be related, if not directly, indirectly, with the bandwidth of the input signal. I say indirectly because there may something may happen in this block as well, which may also influence the bandwidth. The easy example is that this pre-processing block may not give you sharp pulses of ones and zeros. If it does not give that really, okay, then again the bandwidth may be somewhat different. So, bandwidth is an issue, okay, we will look into it whenever it is necessary, fine. What about the statistical features? If the input signal at A was random, is it that the sequence, for the moment if I consider only binary output at this point B, a binary outputs ones and zeros and the sequences of that really, is it that some randomness is still present at this point B? Yes, obviously. Okay, fine. Because this block, the pre-processing block, has or should not introduce any uncertainty, any further randomness. Whatever it has to do, it must do it very regularly, okay, which is pre-decided. So, whatever randomness or statistical features were present in the basic signal, they are not destroyed, okay, rather they are preserved, but represented in a different manner at this point B. Is that okay? So, I can say here is a digital signal which is random in nature. Okay. And now I can also say that this digital signal, if for the time being I am not interested in its voltage level, okay, I can also call it as information. Information bearing sequence, bearing, sorry, bearing sequence. As I mentioned, information has got a meaning, specific meaning in the context of digital communications. There is a whole lot of theory called information theory. We will have a fill of that information theory subsequently. But at this point, when the signal is digital and is random in nature, okay, we usually start associating the word information to that. So I can also interpret this as an information bearing sequence, and this implies that at the moment I am not understanding, I am not very much interested about the levels, voltage levels or the bandwidth. I am more interested about the statistical features perhaps. Okay. So let us go further. I have a blank diagram here whose input I shall now say as information bearing sequence. Information bearing sequence. Okay. So if I forget about this pre-processing unit, can I say that the purpose of a digital communication system is to carry information from the transmitting end to the receiving end? I can say that. Okay. Now, this information can be processed in several ways. I have made two conceptual blocks. I have kept two conceptual blocks for that, this block and this block. Okay. So that the signal B from the previous pre-processing unit will enter this block. Okay. Some processing will be done here. Okay. The output will go to the second block, which is another information processing block. Okay. And the output will be taken downstream to subsequent blocks. I have kept two blocks which will process the information. That means tracing the information part of the input signal. Okay. Now, I can say that because this block is just following the previous signal pre-processing block, if I have to do some information processing, okay, it should better know the property of the pre-processing block and the signal source. Okay. So, if I think of some information processing block, let me call it number 1 block, this is number 2 block. Okay. Then the purpose of this first information processing block should be something decided or guided by the previous blocks. Is that a common sense approach? Okay, fine. That is what you do even in an analog or digital circuit tree. Whenever you design an amplifier, you must know the signal source behavior, bandwidth, etc. for the design of the amplifier, and the purpose of the amplifier is to amplify that signal in terms of voltage or current, etc. So, I am applying the same approach. So, this information processing block, okay, will process the information, okay, which will be guided by the features or limitations of the previous blocks. Okay. The second information processing block, what should be the purpose of this block? Can you guess? Right, very common sense approach. Okay. The second information processing block, it gets partially processed information from the first block. Okay. But then for its processing, it should also look ahead, what are the subsequent blocks really, which will process the signal further. And here is an opportunity. Okay, if I have to design this block, I would like to know what all are to be done in the subsequent blocks before the signal reaches the receiver and it comes to doing some kind of inverse operation corresponding to this block really. It is so wide, we will feel that somewhat later really. So, broadly the first information processing block and its type of processing, nature of processing will be mostly guided by the previous blocks. The second information processing block has the opportunity to do some advanced processing, so to say, which will take care of further limitations or type of processing which may go down the various blocks in the chain of the transmission reception system on the whole. Okay. Let us first talk about the first information processing block. Okay. We have so far identified that this input signal is a digital sequence, information bearing sequence. Okay. Now, and it may be in a simple case of binary transmission, it may be a sequence of ones and zeros. Okay. But when we are processing an analog signal after sampling, now the analog signal, because it has got some bandwidth, the signal is not of a very large bandwidth. Usually it is the case, especially for common forms of signals like speech, okay, to some extent for video signal as well, between two adjacent samples. If I bring back the previous diagram really, when you do the sampling here in the second block, okay, and if the input signal is speech signal, usually it so happens that the two consecutive samples, they do not vary much from one another. Can you guess why? See, if the signal is a speech signal, okay, and if sampling is done at a pretty fast rate, then the difference between two consecutive samples usually will not be very large in amplitude. Yeah, very small. Okay, it is not deterministic, but usually if I sample very closely and the signal bandwidth is not very large, as we know is up to 3.4 kilohertz, in that case the difference between two consecutive samples need not be very large really. Okay. The same thing can be stated in a different form, introducing the randomness in the samples really. See, if I give you one sample, you really cannot predict the next sample for certainty. You cannot say exactly how much is the next sample going to be, but it is very easy to say that the next sample is going to be somewhere close to that. Okay. This property is also indicated by one mathematical feature which is known as the correlation. We say that for many of the signals of interest like speech, okay, the signal samples when sampled at correct sampling rate, okay, the samples are highly correlated. That means the samples are quite similar to each other, and this is one property which can be exploited here. Okay, which means if I know a particular sample of the speech, then I can use some technique by which I can guess very correctly, very closely what the next sample is going to be. And there has been a lot of activity in this area, okay, which exploits basically the correlation which exists naturally in the signal samples, especially when the input signal has got a smaller bandwidth like in speech signal. This correlation is present highly. So, this correlation can be used, okay, and then some kind of processing can be done accordingly such that we can save the number of bits in a binary transmission which actually have to be transmitted. I go back to the next diagram. My point is that if I now look at this input sequence of ones and zeros, okay, if I have two very similar samples and if I quantize and code one sample by 8 bits, which is a popular standard, we will talk about that, then two subsequent samples from the speech signal is going to be almost of similar height. There will be minor differences. Okay. So, if I think about their binary representation where each sample is represented by 8 bits, then I can say that for two samples there will be 16 bits coming one after another, okay, and these two groups of 8 bits will vary only in the LSBs, second LSBs and things like that usually. That is what is because of strong correlation. Okay. So, if it happens like that, then at this point there is another possibility. One possibility is that make use of that correlation, okay, exploit this correlation such that the bit stream that comes at this input point, okay, can be made of lower rate. Bit rate, when the information is represented in sequence, no more in analog signal, we talk about bit rate. Okay. So, if I think about a bit rate at this input point, say R of B, RB bits per second, then it is very useful, we will appreciate subsequently, that any processing which can be taken up for reducing this bit rate, so that I get a bit rate RB prime at the output of this processing block, which is less than the previous bit rate, then it is a meaningful processing. I repeat, the information bearing sequence will have a bit rate RB bits per second. Now, if I can do some kind of signal processing here in the digital domain, so some digital signal processing here such that at its output I get an effective bit rate RB prime which is less than the previous bit rate RB, then I can say this information processing is meaningful. Can you quickly guess why? Because when I have to transmit this signal, okay, then the bandwidth that will be necessary is going to be less than what would be necessary if I would not have done this operation here. Okay. So, a very important and major purpose of this first information processing block is to do some kind of processing in the digital domain, okay, some kind of digital signal processing such that the effective bit rate is reduced.
What is the connection between bandwidth and effective bit rate? Number of bits.
There is a connection. The bandwidth of the signal, okay, dictates the optimum sampling rate, okay, and then when you decide about how many levels are to be there after quantization, you effectively get the bit rate after quantization and sampling. Okay. So, the bit rate is decided by the number of quantizations and the input signal bandwidth through the sampling rate. So, they are related. Okay. What I am now talking about is whatever has been done beforehand is fine. Okay. Now, starting with this input sequence at a particular bit rate, if I can do some further processing by which I can reduce this bit rate further, that is a net saving perhaps, that is going to be of advantage all through the design of the subsequent modules and even for transmission. But there is one word of caution really. In trying to reduce the bandwidth, I should not compromise with the quality of the signal. I should not go for some kind of processing by which the basic signal, because I have to reproduce the signal back somewhere in the receiver, there is no distortion because of this signal processing. Okay. Now, in practice, there are two major approaches to this method of reducing the bit rate. One approach is known as a lossy coding scheme, source coding scheme, wherein some level of signal quality degradation is accepted. There is another class of source coding scheme wherein no loss is involved. Okay. We will in this course discuss about a few lossy schemes, source coding schemes, and we will discuss about at least one lossless source coding scheme. So, this block, the first information processing block, is known sometimes as a source coding unit, source coding block. The name implies that the focus is on exploiting the features of the inputs information bearing sequence. Okay.
Sir,
yeah, please.
how does this reducing bit rate take help of the correlation that exists between the two subsystems?
We will study that. We will study that. Okay. We will see that if we go for a differential PCM from a PCM approach, we are actually making use of the correlation among the samples really, and because of that we can reduce the bit rate by half even. Okay, we will see that. That is a topic we will cover. Fine. So, the purpose of the source coding block is to reduce the bit rate from the input bit rate. Let us come to the second block. The second block is known as channel coding block. Channel coding block. Okay, as the name implies, it tries to take care of some of the possible problems in the channel. Okay, but the channel that is implied here is actually not the physical channel that I showed here some time back between the transmitter and receiver. This channel in this example of a wireless communication system may be free space or something close to that, is it not? Okay, between two transmitting and receiving antenna. This channel word, as I mentioned, is again something which brings in ambiguity. So, we will have a brief discussion about what kind of channel we are actually talking about. For the time being, let me mention that the channel implied here in this block is a discrete channel, Okay. We will have a map of that really after we finish this discussion in a more conventional way. Okay. So, the channel here you can note is a discrete channel. This channel is different from the earlier channel, and this does not take much time to justify that, because I can say that at least for this wireless communication example, if I consider this point as the input to my channel, then this signal here is some kind of analog signal, analog waveform. Okay. The signal that is given by the channel, that is a channel output which is accepted by the receiver, again is some analog channel. So, this channel, the way I drew over here, is a channel which accepts analog waveforms, which delivers analog waveforms. So, this should be called as an analog channel or waveform channel. In contrast to that, in this discussion, the input to this channel coding block, what kind of signal is being fed here? It is a digital signal. The output is also digital. Okay. So, the signal in terms of signal that we will get here is again a digital signal. So, this block is a digital in digital out block, which gives you the opportunity to go for digital signal processing. Okay. But the purpose is to take care of certain problems which may occur down the stream. Fine. Summarily, the major purpose of this block is to safeguard the information bearing sequence against any possible distortion or error in information that may take place during transmission. I repeat, the purpose of this channel coding block is to safeguard the information bearing sequence in an appropriate manner, so that we receive the correct information sequence, okay, against any information error. The term error again I am using for the first time. Okay. Errors usually occur because of problems of noise, interference, etc., which and other forms of distortion which may be present during transmission and reception. Yes, please. Yes, yes. Now, the major approach for safeguarding information sequence in this block is to add some information generated from the information sequence following some technique. Yes. Another question?
Does that imply increasing the bit rate now?
It does. It does. Okay. So, the major purpose of this channel coding block, which is a digital signal processing block, is to ensure as much as possible within the constraints, given constraints, to ensure the sanctity of information sequence, okay, which is to be transmitted through the physical channel, okay, against any possible noise interference, such that there is no error in the information sequence when the sequence is recovered and delivered to the end user at the receiver end. Okay.
When transmission we can transmitting and send discrete signals.
Yes.
How is this discrete channel?
Well, Your question is, I mean, in a baseband transmission form, okay, the channel itself may be viewed as a discrete channel. Not necessarily. It depends on, in fact, we will also model this channel in this diagram, okay, not this physical channel only, incorporating certain other modules of transmitter receiver, and will show that it is possible to identify a discrete channel even in this case of carrier modulation scheme. Even if we do not use any carrier, okay, we can also identify a discrete channel. That is a question of modeling basically. I'll come back to this point. Yes.
So why is the channel input is analog and output is digital? Output is analog. Why can't input and output both be digital to the channel?
Your question is that, could you hear him? His question is with reference to this diagram, why should the input to the channel be analog and the output from the channel should be analog? Can it not be digital? Okay. Any quick answer from any of you? That's the answer really. Okay. You can try to transmit digital signals, okay, but for communication systems you are very pressurized in terms of transmission bandwidth, the amount of bandwidth that you are utilizing. Okay. The problem is not very same if you are designing a radar system where pulse transmission is a very popular scheme. You can transmit pulses, but for communication systems usually it is a CW transmission scheme, continuous wave transmission scheme. Okay. That is how you require minimum possible bandwidth, and utilizing minimum possible bandwidth is a very important issue in the design of the system. Okay. So, coming back to the channel coding scheme, the purpose is to safeguard the information sequence, okay, such that we any information error during transmission reception can be avoided, and correct information sequence as much as possible. I say as much as possible. It may not be possible to correct all errors there. There is a limitation, but within the limit some errors are corrected and the good quality information sequence is given to the receiver user. Okay. And one major approach for that, as your friend suggested, is to add some more information, more bits to this really. Okay. Now, we will have a very brief feeling of the kind of information addition that goes over here in the name of parity, etc. Okay. This again is a very important issue and is broadly known as the subject of error control coding. Error control coding. Okay. So, we will have brief discussion on this module. So, the output from this block is digital in nature. Now, those of you who have studied analog communication systems, try to suggest what should be done in the next block or subsystem. The input is a digital sequence bearing information with some safeguard against possible errors. Yes, convert to analog form. Okay, okay, and how can we do that? Yes, right. Okay, so I accept both the suggestions really. This block we are going to name, just for our understanding, as a baseband pulse shaping unit. This is a very important operation in digital transmission scheme, especially for wireless communications. Baseband pulse shaping unit, you can say. So, the output of this block should be analog or digital, analog waveforms. Okay, I should say analog pulses. The analog, the digital to analog conversion, I mean, even if I talk it that, I mean, mention it that way, that goes in this unit is not the same as AD converter or DA converter. Okay. The purpose of this block is much more interesting really. In fact, we can call this as a part of modulator as well. In fact, for many of the digital modulation schemes we will see later, the major issue is done here itself. The pulse shaping forms a very important part of digital modulation scheme. Okay. And the output shaped pulses can be directly taken to a modulator, carrier modulator, okay, where we use the carriers to translate the shaped pulses at that respective intermediate frequency level.
Can you show them what kind of the output of this block will be?
Right. Okay. Let me say, if this is a typical pulse, what we get here is a sequence of pulses once again. So, I am considering one pulse here. Okay. Maybe after shaping, baseband shaping, we generate a pulse something like this, which is a pulse shaped compared to the earlier one, okay, such that when it comes to measuring the bandwidth of a random sequence of such pulses at this output, the bandwidth will be much less compared to the bandwidth of the input signal. Not only that, the basic mechanism of modulation also can be incorporated here itself. We will see. I mean, this is going to be a very important topic for us. We will talk quite at length about this particular block. This is a part of the modulation scheme. Yes, please.
What kind of modulation are you talking about? Is it, digital modulation by digital schemes or
modulation by digital scheme? Okay. Our discussion is totally for digital communication systems. Okay. So, we will find for almost all forms of digital modulation schemes, this block has got an important role to play. Okay. Baseband indicates that the signal or the information bearing sequence has got a bandwidth start at the low frequency end of the radio spectrum. Baseband, I think those who have studied analog communication can also say that the it's not yet used for, not yet ready for modulation. Okay. In fact, it is, I am effectively talking about the modulating signal. If you just quickly think about the analog counterpart, really, an analog modulator has got a modulating signal. This modulating signal also can be called as a baseband signal or low frequency signal, okay, which is yet to be coupled with a carrier. Fine. When you couple it with a carrier through modulation, what we get normally is known as an IF signal, intermediate frequency signal. Okay. I have mentioned it here in the diagram later. So, this baseband term is very popular in the context of digital communication systems especially. Baseband signal means it is a relatively low frequency signal still. So, if you are interested about the spectrum of the signal at the output of its at point E, you will find a signal whose bandwidth is at the lower end of the radio frequency spectrum, maybe from 0 to certain hertz in one sided representation, a few kilohertz, a few megahertz kind of. So, this is a part of modulation scheme really. The next block is, I can say, is a carrier modulator, CARRIER modulator, wherein we use a carrier say at f1 frequency, and the usual carriers are sinusoid in nature. There is some similarity, yes. Okay. If the modulation in the digital domain is in amplitude, yes, it is somewhat similar to amplitude modulation, yes. Okay. But we will see that there are many other interesting forms of digital modulations which are closer to phase or frequency modulation in analog domain, and many suitable combinations thereof really, amplitude as well as phase modulation and things like that. There are more number of digital modulation schemes, okay, and to choose from really, depending on what you have to satisfy and what kind of channels you have to use and things like that. Okay. Yeah.
So the current is the same scheme that analog communication. With a different format.
What I say is that the schemes are somewhat similar, but they are not identical.
So why not identical? So very different format. Simultaneously analog.
The difference is this analog pulses at point E, I would not like to call it as analog signal only. I would rather call it as information bearing analog pulse sequences. So, the theme is that what is to be conveyed is still information. We should not go for any kind of processing down the stream which distorts the information. We are not allowed to do that. Okay. So, that way there are differences. We see that there are also differences in how you implement it. Okay.
So does that mean that the system you're using for modulation is more sophisticated than the analog part?
We did not call it as sophisticated really, but I mean yes, actually in terms of end-to-end quality, okay, it is possible to achieve much better quality if you are using a digital communication system rather than an analog communication system at the same cost. So that way, yes, things are sophisticated, and that's one reason why digital communication systems are becoming more and more popular in deployment. Yes, okay, but the reasons are several. The reasons are distributed in all these blocks, and when it comes to designing a particular block, you will find that there are many design parameters to trade off, to balance, to achieve a particular goal. So between end to end, you can ensure the quality that is that is necessary, okay, by bringing in modifications at various places really, which can reduce the cost of the whole system, which will require minimum power for transmission, and which may require a reasonable amount of transmission bandwidth. Okay. Yes, please.
So the pulse shape of the analog signal that we are getting there,
Right.
does that help in doing the perform the carrier modulation? Because we are using different techniques. So are these techniques especially for the pulse shape, related to the pulse shape of these analog signals?
Mention a technique, one or two techniques that you are talking about.
Yes, sir, you have said that there are special techniques for digital transmission and digital carrier modulation.
Right.
That are especially for the digital.
Right.
So just are they related to the pulse shape of these analog?
They are related. They are related. What we will see later is that in a pulse, okay, to get back our information somewhere in the receiver, we will be interested at one sample instant, one time instant in the pulse duration really. Okay. So the techniques for doing that have to be developed in the receiver. Okay. They are different from analog demodulation schemes. So there are many differences. Okay. New techniques will come in over there, but here when it comes to carrier modulation, there is a similarity with analog carrier modulation also. Okay. But in implementation, there are differences. The same chip which does the analog modulation may not do the digital modulation equally well. It's something like that.
Is it vice versa? If we use for digital modulation,
Right.
we use for analog ones.
In some cases, yes, it may be. Not in all cases. Okay. Those are the finer details about the specifications. In fact, the manufacturers, they design the ICs with some applications in mind. There are ICs available, okay, which are good for some low bandwidth frequency modulation, narrowband FM, which are also good for one digital modulation scheme known as FSK, frequency shift keying. Okay, because things are very similar. It has been possible to design an IC at a low cost. So there are ICs available really. Okay. Now let us go further. So the next block, as I mentioned, is a carrier modulator, wherein we bring in an carrier. We call this as the intermediate frequency carrier. Okay. So the purpose is the purpose understood? The purpose is to take this low frequency or baseband signal up to an intermediate frequency. Okay. And usually these two blocks taken together form what is known as a digital modulator. These two blocks together, digital modulator. Now tell me briefly, what is the nature of the output signal from the carrier modulator? Is it an analog signal? Analog continuous wave. Okay, continuous wave signal. Okay, if I try to see on the CRO, things may look closer to sine wave or cosine wave, okay, with some variation in amplitude or phase or something, okay, because I have used the carrier over here, sinusoid carrier here, okay, and this signal has got a bandwidth, okay, which is dictated by the bandwidth of the input analog pulse stream and also by the nature of modulations. Like for the same modulating signal, even for analog communications, if you are using FM, the bandwidth becomes larger. If you are using M, the bandwidth is something, AM, DSB or SSB, isn't it? So somewhat similar to that. I mean, depending on the bandwidth of the basic analog pulse stream, that is the baseband signal bandwidth, and the type of modulation scheme that is being used, one can get an idea about the bandwidth of this modulated signal. Okay. But a very important feature at this point is that the signal here can now be called as a band pass signal. Is that okay? The signal here is a band pass signal. The signal here is a band pass signal. That means the signal center frequency is at the modulating carrier frequency with a certain bandwidth. Okay. Now, usually the bandwidth of this band pass filter is much smaller compared to the center frequency. Okay. Usually that is the case in analog communication also. And when the modulation scheme is something like that, we say that the modulation scheme is a narrow band modulation scheme. Narrow band modulation scheme, when the bandwidth of this signal at this point is relatively smaller. A thumb rule is within 10% of the value of the center frequency, we say that modulation is a narrow band modulation scheme. There is a counterpart which is gradually becoming very popular now, which is known as wideband modulation scheme, for which the bandwidth after modulation is going to be quite appreciable, maybe around 10% or even more in some cases compared to this modulating carrier. Okay. Our discussion in the course will be wholly on narrowband modulation schemes. Let us stop here today. Unless you have a question, we will continue from this point onwards. I will request you to think individually about what all may be the functions of these three remaining blocks. Any question?